So, introduce yourself and go on.
Okay, thank you, Per. As I'm happy to present you the password hashing competition, the project that will hopefully ruin the business of Jeremy. You won't be able to crack passwords because we'll have better functions. And as you've seen in the previous talk, many services could use MD5, SHA-1, sometimes with a source, sometimes without. We even see things like this. People really from that they should use hash functions, not use functions, but they still store passwords in clear. So the goal of the password hashing competition is that everybody, all services, use strong password hashing, use strong password protection methods. So I'm originally a researcher, academic researcher. I'm now working for a private company, and I've been part of the recent SHA-3 competition organized by NIST, and prior to that, the eStream competition, which was about block ciphers. When the ES competition was run, I was not in the game yet, but I can talk to you about this as well. So the idea for cryptography competition is that the organizers, they choose a type of cryptographic primitive, the block ciphers, string ciphers, hash functions, public encryption, and they publish a call for submission. So say, we would like to receive this kind of design with these properties, and we evaluate it according to this criteria, security, performance, and so on. So people are happy, they submit things, and they are evaluated by a panel by researchers. And if you look at the incentive, the goal of people of submitters to grade the others. So people publish research, they publish papers about security analysis, performance analysis, and so on. The organizers shortlisted the submissions. In the case of SHA-3, it was approximately 14 out of 54 received. And after 14, they shortlisted to 5 finalists, and they eventually picked one. There was AES, 97 to 2000, block ciphers, 15 submissions, 5 finalists, and right at the Belgian ciphers for the competition. It was eStream. You may not have heard about it because it did not give a formal journal, just recommendations. Maybe you know the cipher starts at 20 by Dan Bernstein. So it's one of the winners of eStream. And it's just very more recent. It was won by Ketsak, so it's designed by the same guys as AES, it's Rindle. And it was 51 submissions. So as I said, it's basically demolition derbies. To create evolutionary analogy, you in this game, you try to beat the other designers, your submissions, and at the end, the organizer will pick the one that survives. It's not the survival of the most secure or the fastest, but really the one that is the most adapted to the environment, the needs of the users, the requirements as perceived by the organizers. If you look at SHA-3, Ketsak was a really good function, but the others were also really good. Maybe some other were a bit faster, a bit simpler, a bit more secure. But according to NIST, Ketsak provided the best balance with respect to their criteria. And if you look at the side of contributors, so academics, they really like it because they're going like to publish the best papers, publish a lot of papers of good quality. This is a good opportunity to make great research and to publish it. When I made the count for SHA competition, there were more than 50 academic formal research papers published due to the SHA competition. So they get better reputation, they publish good research, more papers obviously, they get money from the governments, and it's a lot of fun to attack your colleagues' designs. Okay. So it's basically free work for the organizers. And free work was millions of dollars. So that's great for NIST. Most of the contributors were Europeans, and the reason that the work was to Americans, Europe. So that's great for NIST. So we have AES, Stream, SHA-3, and we have PHC and CIDA, which is about authenticated ciphers. That's not the topic of the talk today. Okay. So, as per mentioned, PHC is starting now. Well, we published a call for submission in January. I mentioned that I created this, but I only mentioned the idea on Twitter, because I see all these people having great ideas, great expertise, and after Shastri, when I came with my academic background of cryptography, I said, well, that's the best opportunity to create a new competition. We really need something better. We have the knowledge, we have the expertise, and we have the need from the market, let's say. So that's the perfect time to start this. And people were very enthusiastic, very happy and proud to have people like Jeremy, like Swag Designer, like a few people around in this room. So I really tried to have the best people, but the people who would be the most helpful for this competition. It's not sponsored by any organization or any company. We don't receive any money from anyone, so we have no bias. We are neutral, try to be neutral and objective. And the panel that I was mentioning, we have a list of approximately 20 people from industry, academia, and even the US government that matter from NIST, from the crypto group of NIST. To have crackers, people who know how to protect passport, which means they know how to evaluate the security. They will be able to know whether this one is easy to implement on GPUs, whether it has a good attacker to defender ratio. We have software engineers, we have cryptographers. So the goal was really to have the best mix of people to evaluate the submissions. We don't want to miss anything, because if you look at previous competition, sometimes, in my opinion, they were a bit too focused on cryptography, which means that we have submissions that were very good from an academic point of view, from a theoretical point of view, but that missed some points for being used in practice. So one of the motivations, I don't think I need to repeat myself, you know everything that happened in the password hacks. So one of the typical argument is, okay, just use the creator script. You've heard about the creator script before, so I'd like to provide a bit more details and to explain why script is not perfect. As a matter of fact, script is not used a lot. It's today in DARSnap, which is the system of coding for Civil, who designed script. I believe it's used in a few other systems, but it's not as popular as SHA-1. It's even much less popular than Decrypt. Decrypt is used, for example, by Twitter, by Living Social, by a few other systems. But nobody uses Decrypt, nobody uses script. I've had the question why. Let me briefly summarize how script is working. The idea of script is to force the defenders and for the attackers to make a lot of operations and to use a lot of memory. Like someone said before, using a lot of memory is not just about allocating a huge pool of bytes, but also making many accesses and unpredictable accesses to this memory. So the first step in script is to initialize a large array that you fill with random values. These values that should depend on the password, otherwise you can pre-compute it and it would be completely useless. Now that we store this in memory, and the second stage is to make unpredictable accesses to these elements. So you can have predictably advanced switching and multi-will access, and this pattern aims to be pseudo-random, and this pseudo-randomness is seeded by the password and the source. Okay. So why script is not used a lot? So in my point of view, one of the reasons that it's really not simple to understand and to implement. I don't know if you've read the research paper by Colin on script. So it's really a good work with some really interesting attempts to make it more formal, more scientific. There's a lot of insights, but it's quite sophisticated. It's not really accessible to developers. And if you want to implement script really from scratch, so you have to look at two main components, SMIX and MFCrypt. SMIX is a procedure that uses another procedure called RUMMIX, which itself embeds BlockMix, which eventually calls SASA28, which is the core algorithm of the SASA20 stream cipher, which I mentioned before. And then you also have to implement MFCrypt, which uses UDF2, which is HMAC, which uses SHA-256. So you have to implement 1, 2, 3, 4 cryptographic primitives, as well as these procedures. So it's a lot of code, a lot of bugs, a lot of tests, a lot of time. Not sure that all organizations can afford this. So maybe they will pick an existing model. You have model for script in C, in Python, and languages. Now you have to integrate it in your application. You have to choose parameters. There's really three parameters, N, R, and P. N is the integer walk metric. R is the block size parameter. P is the partition parameter. But R also affects the parameters of the function. So from that point, you might guess that P does affect the ability to make parallel implementation of script. It's not clear whether it's at the local level using SIMD units or for example, multiple. It's not important point. Is that matter what are the objectives of N and R? So what metric you can get if you increase N, you have more work to do, more time, and or more memory. R seems to be the block size is probably the size of the blocks that you're written memory. So if you don't think too much about it, you look at the parameters specified by encoding speed variable size. There's a few recommendations. As far as I remember, 2 or 3 or bit more sets of parameters. But maybe you have very specific applications, maybe you run it on a mobile phone, maybe you have unlimited memory, unlimited time. You really like to have the best parameters for your application. So I want to understand how is affecting the performance of script. So actually N and R have essentially the same effect on time and on memory. You can make N times R basic operations. So the question is the time works linearly with N, linearly with R, the same factor. And memory is also NR 128 So it's exactly the same influence theoretically on time and memory consumption. And I made an experiment on a CPU, on a recycle bridge. And the color is the actual time spent to hash a password. On the y-axis you have the logarithm of R, and then the logarithm of N. And you see that you have exactly the same pattern if you go vertically or horizontally. I'll let you move for this, but I don't think you need to say it. I will show it in my backup talk, but just to show that this works. That means that it's no difference if you double the value of N or if you double the value of R. So you are a developer, and from your point of view, N and R are exactly the same thing. You don't know what's happening behind you don't understand how N and R will affect differently the attacker with the GPU or with its ASIC. You just care about your application. Another problem that is mentioned here that maybe you have limited memory, so you want to be extremely slow. You don't have any latency issues, you don't have any latency constraints, but you have memory constraints. And with script, it's not possible to make it slower without increasing the memory consumption. And the other way around. That's my point of view one of the issues with script. The other issues being the size of the code, the number of components you have to use, the fact that you have to reuse PBKDF2 to understand how all those guys work, and also that you have to choose parameters. So what I would expect from the PhD competition is designers to come up with more simple things, with maybe 2 parameters, one for time and one for memory. And if you increase the parameter of time, memory remains constant, and the other way around. It's less easy to do than what it sounds, but that would probably be the easiest to understand for developers. Because we don't want to blame developers for not being experts. We are the experts, the developers are developers. Okay. So I believe we do something better, and that's why we have these thoughtful submissions. We have very simple requirements. We want your function to hash passwords. So to take strings of bytes. We don't make any assumption on the encoding. It might be ASCII, it might be Unicode, it might be your own proprietary character encoding scheme. We don't really care about this. Hashing data, hashing bits, hashing bytes. We make the assumption that, 128 is already a reasonable size. You may support more than that, but this is what we want your function to support, at least. Also, one function to generate a 16-byte, to use a 16-byte sort. So you might support shorter or longer sorts. That's what we need to be a reasonable length. So we want the function to support sorts of 128 bits and at least one cost parameter. It might be cost, it might be time or memory or mix of both. But in the API we specify, you should at least have one cost parameter. We don't make the assumption on how it behaves, if the speech should go linearly or exponentially. That's up to your design. And it should have just return a hash of 16 bytes, or more or less, but at least 16. This could be generated with respect to a few criteria. The first obvious one is security. How we define security for a password hashing function? So we know how to define security for a block cipher. You should not be able to decrypt, it should be secret. We also pretty much understand how to define security of general purpose hash functions, no collisions, no parameters, indifferentiability from a random variable, all those great notions. But for password hashing functions, what do we expect? So first, it should be one way. Given the hash, you should not be able to go back to the password that's used. And you shouldn't be able to go back to any other password or string that maps to this hash. And it should also be pseudo-random. The pseudo-random is generally defined in terms of a key hash function when you have a secret. And when the secret is known, you make order queries with a function. And you should not be able to distinguish the output from true or ideal perfect randomness. We don't need really to consider very formal notions, but there should be no properties that make the hash non-random, whatever non-random is. Like also presented before, it should minimize the ratio, should minimize the advantage of the attacker. So this is your job to define how to define this ratio, which is a difficult problem. And because parameter should be effective, it means that if you claim that the hash function has to use 1 meg of memory, there should be no way to bypass this requirement. And it should be flexible, scalable, and to some extent resilient to side channels. Simplicity, something that is often overlooked by professional cryptographers. They make very sophisticated design, very clear algorithms, sometimes with things like fast rate transforms, commutative algebra. But what you just want, what you just need is something simple, at least easy to get right. So it's not just about the specifications, but also about the implementations. Regarding specifications, you don't want to assume that the reader knows about advanced mathematics or has 10 PhDs in maths. And about implementations, it should be easy to translate, get the spec to code. And like Russell said before, it would be great if this reports instructions from the CPUs and you don't have to emulate an operation with several instructions. Design choices, I don't have much time, I'll skip this one. And I'll go to maybe the most interesting part. So the to-do items, let's say. First one for cryptographers. I'm not very happy about the state of research. Maybe it's because the problem is too applied or is not maybe formal or mathematical enough, but there's been very few research by academics on this. Fewer than 10 serious research papers. So I would like to see people getting interested in formal constructions of password hashing schemes, in defining notions, defining formally what is a password hashing scheme, what is the security of the password, hashing scheme and how to prove secure constructions that use an arbitrary hash function, for example, like SHA-1, SHA-2, SHA-3, and that uses this hash function to construct a secure password hashing scheme. That's what ubiquiti 2 and script try to do to some extent, but we can do much better than that. And the academics, they will also look at dedicated hardware architectures and obviously cryptanalysis. One of the challenges, maybe more for software engineers or password crackers, is to predict the future, which is known to be a difficult task. The problem is we don't know what will be hardware attackers in 10 years. Even 2 years is very difficult to predict how will the next generation of graphic card look like. But we don't want just to protect users today, but in 5, 10, or maybe 20 years. And we want to minimize the advantage of attackers, not just today. So for example, you might want to exploit the latest feature in Intel's microarchitecture as well, where you have these nice 256-bit registers. There's some crazy functions. There's SIMD memory lookups, EPRMD, which is very good for crypto primitives. So you might take advantage of those to minimize advantage. But maybe the recently announced APX 512, you can also find good instructions to use the password hashing scheme. And in the future generation of Intel, there will be another new set of instructions. They should settle something and choose what's the best balance. Another issue is leakage resilience. So, simply site and resistance. Let's say you use a huge table. Maybe you've heard about cache timing attacks, and that information on the secret can leak from the access pattern, from the time use, because depending on the cache line you access, you have a different latency value. So the idea is that if the pattern of memory lookups is dependent on the password in an invertible way, you will get information on the password if you are able to monitor the memory lookups. So do you expect your user to write their memory after they have the password? Do you expect the hardware to be totally tamper-proof? You have to make the assumptions you make on the attacker in your submission. And obviously, if you support password of arbitrary lengths, you will have timing issues because with a password of 1 million characters, it will not take the same time as the same characters. Cancel hashing is a very challenging problem. In your service, if you force the server to make more competition, to use more memory, then you might expose it to the risk of the OS. Maybe that depends on the application, depends on the server, depends on the infrastructure. But I don't think that should be enough. And finally, updatability. Let's say you have a set of hashes of 1 million users, and you update the new hardware. Instead of having one server, you have a much more complicated system, much more powerful servers, much bigger cache, much faster CPU, and you want to make stronger hashes. You want to take the same time to hash a password, and given your improved hardware, you can afford using more iterations, more memory. So how do you directly go from the hashes to stronger hashes? You might ask your user for password reset, or wait until all the users reload to your service. It would be great if you could offer this kind of functionality directly, upgrade hashes to stronger hashes. There are other ideas, some crazy ideas like programmable hashes. Here the idea is that the ghost parameter does not define just the number of iterations, but it really defines the hash function. And if you think about it, it's like a code generator for a virtual machine. You take a password you solve, and from this you generate a program that is interpreted by a VM. So here the problem is interoperability, performance consistency. I'm not sure it's a good idea, probably not, but maybe you can think about it. Another crazy idea is security robustity. The idea is to take your hash database of maybe 1 megabyte and and millions of daily values that even if not occur for the database, you won't be able to figure out which one are the legit hashes and which are the fake ones. Okay. Again, this sounds like a crazy approach. Maybe it will work on some systems. Probably it will not work for all systems, but again, we can probably think about it. Okay, so I'd like to here and this is the conference that Bear Candy was supposed to organize in December. It's only the same temperature as outside this room, maybe the same as in this room. Yeah, I think the idea is to make it a bit more, not more academic, but yeah, but to get more people interested from the academic area.
Now we are at final talk, so you actually have to pretty much leave the room now, so there won't be any time for questions at this point in time. But I have to ask you, would you like to come to our party at our place tonight at 8? Yes. So there will be an opportunity to talk to Jean-Philippe there. And now